Welcome to a quick overview of some ideas for helping you with your climograph data. So these figures are going to be going over some of the key ideas from the different modules that you've taken notes on and how you can use them to understand the analysis questions that we are going to be using to understand why a certain location has a certain climate. So for Module 9, some key ideas that I think are important are the following. The first is that the Earth is a globe, so it's going to receive different amounts of sunlight based on its latitude. That is based on a couple ideas. A, solar radiation is going to hit the equator most directly and most concentrated, which is going to cause temperatures closer to the equator to generally be warmer. The further north or south you go from the equator, the more dissipated that light will be, so temperatures will generally be colder, assuming all things are equal. Further, because Earth isn't actually on a 0-degree axis, but is tilted to a 23-degree axis, that means the amount of sunlight that locations get throughout the year vary based on the proximity of that location to the sun. We know that in the winter, Vermont gets less sunlight than in the summer, and that is the opposite in terms of the calendar months in the southern hemisphere. Another thing to keep in mind is that as you move up in the atmosphere, pressure due to gravity decreases, which means that gas molecules are spread out further apart. Because temperature is a function of kinetic energy of the molecules in the atmosphere, that means that generally as you move up in terms of elevation, the more dissipated gas molecules hold less heat and as a function have less temperature. Because of that change in temperature and heat, we generally see drier air as a result of elevation as well. Colder, drier air with less precipitation is pretty consistent across all mountains throughout the world. Another way that we can think about Module 9 is the impact of ocean proximity. And this is more important when we consider ocean currents in a few minutes. But generally, as you move inland, temperatures tend to be warmer and colder at the same time and at the same latitude based on the idea of oceans being a heat sink and heat source. This has to do with albedo. Albedo is the measurement of reflectivity of solar radiation based on the surface type of the Earth. A higher value means more reflectivity, and a lower value means more absorption. Oceans have a reflectivity of about 5 to 10%, so they absorb a lot of solar radiation relative to grasslands and some forests. This means during the day, an excess of heat will be absorbed in the ocean, causing nearby lands to be not as warm. This is a heat sink relative to the land. However, if you're inland, that is not the case, so temperatures will rise dramatically. At night, the opposite will be true. Because there's no heat source, the inland temperatures will drop precipitously, while the excess heat stored in the water will move to the colder areas near the coast, becoming a heat source. Now, in terms of Module 10, which has to do with atmospheric circulation, there are a few ideas that I want to cover that might help you with understanding how weather moves through your locations. The first idea is the Coriolis Effect. And the Coriolis Effect is that the Earth, because of its spherical shape and its rotational orbit per day, does not mean that objects travel in a straight direction if they move north or south. Rather, if an object is moving from the North Pole towards the equator, it will be going from a slower to faster region. Hello, is it okay that I'm in here for a sec? Okay. What this means is that we're playing catch up as we move towards the equator. This is going to cause an object to shift to the left or appear to be orbiting in a clockwise rotation because the place that it would have gone if it had traveled straight is theoretically spatially ahead of itself. Now the opposite is true if you move to the southern hemisphere. Let me rotate this image oppositely. If we now look at this image as if we were looking at the South Pole, the opposite is going to be true. So things are going to be moving in a counterclockwise rotation. They would be flowing in that direction. What this means is that when we look at weather patterns and the other two figures, weather does not move up and down, north and south in a straight direction, but rather in a three-dimensional sphere. The main ideas that we need to feel comfortable with when we look at atmospheric circulation is that at the equator, because of the maximal amount of sunlight, this is going to be where we have high pressure causing, or low pressure causing weather to move from the surface up to the upper atmosphere. Because air is moving from a warm surface to a cold atmosphere, it will condense and cause precipitation, causing a lot of rainfall at the equator. That air, which is now cold and dry and high in the atmosphere, will be pushed further by more air rising, and it tends to fall at the subtropical high pressures at 30 degrees north and 30 degrees south. We call this high pressure because the air is literally falling on us rather than rising up. These tend to have really dry locations. Due to the incredible lack of sunlight in the poles, we tend to also see really high pressure at the north and south pole, which causes really cold, dry air to flow downwards. When we look at our global atmospheric convection current, the first convection current, known as the Hadley cell, is going to be operating between 0 and 30 degrees north and south. The air will flow upwards due to low pressure and equatorial warming, and then flow downwards at 30 degrees north and south. The air then will return, being sucked in like a vacuum because of the low pressure here, and that's going to cause air to deflect downwards in either a southwest or northwest direction. And this is happening because we're going from a slower to faster place. Alternatively, if air is moving northwards at the subtropical high in the feral cells, they're going to be going from a fast to slower place. So they're going to be not catching up, but going ahead. They're going to be pivoting to the northeast or the southeast. This is why when we look at a lot of weather happening in, say, Vermont, a lot of it comes from the southwest and heads to the northeast. Polar air interacts with the feral cells, and depending on the season, this air might be weak or strong. Tends to be stronger in the winter, weaker in the summer, and this is going to cause air to interact here, and that causes air to rise at the subpolar lows. This is also where we have a lot of precipitation. We can look at what a high and low pressure system looks like with this figure here. This isn't drawn completely accurately because it shows a counterclockwise and clockwise pressure system in the same atmosphere, when indeed it should all be the same. But in a low pressure system, we tend to have a lot of warm air rise and cool, forming rain clouds and precipitation. That low pressure is like the suction thing they put in your mouth when you go to the dentist. It's sucking things upwards. As that air cools and dries, it will rain. It will be continuously displaced and eventually fall due to gravity. That cool, dry air will form high pressure systems that tend to be sunny and quite mild, and that air will then be pushed out and be sucked back into another low pressure system. So it's sort of a convection belt. The most important thing to know about your locations is what cell do I exist in, and how does that influence the direction of weather in my system. We finally move on to ocean currents, and ocean currents are driven by atmospheric currents. So if you're in the northern hemisphere, ocean currents tend to flow in a clockwise direction, and if you're in the southern hemisphere, they tend to operate in a clockwise direction. A ocean is composed of one or more gyres, which is a conveyor belt of water, and they tend to be either warm currents, which tend to be surface level waters that are driven by warming at the equators, or cold currents, which means either deeper oceans or colder water that are moving from more northerly or southerly latitudes back to the equator. At locations next to, adjacent to southern colder currents, the climate tends to be a little bit colder and a little bit less dry, or less wet, more dry than other places at the same latitude and elevation. So, for example, California and Oregon, as well as Peru and parts of South Africa, tend to be a little bit drier and cooler than their counterparts at the same latitudes. Alternatively, warmer ocean currents that bring warm water from the equatorial regions tends to result in wetter and warmer weather and climates for latitudes than their counterparts. So if we go to England, which is noticeably more north than New England, they tend to have a more temperate and warmer weather pattern than New England. And this is because all of the Gulf Stream is bringing warm, wet weather upwards. And again, this is being driven by the movement of atmospheric currents occurring based off changes in pressure and heat. This might have helped. I hope it has. If you still have more questions about more specific topics, my next reference point would be going to AP Classroom and looking at the specific videos for each module. Have a great day.